it's 100 million times faster. They kiss, come on! You kiss! So this works at an organic level. It also works on a biochemical level, and this is one of the cool side effects of binding. If we imagine our cute little kind of Pac-Man-y enzyme, and it's an enzyme that's supposed to take glucose and ATP and react them together. If glucose and ATP are just floating around, the odds of them running into each other is really low. If you shove glucose and ATP into this small cavity, the odds of them bumping into each other are really, really high. So we can effectively push things together. Proximity is also called effective concentration. Effective concentration. And here's why. If we have a box that has one glucose and one ATP, and the box is, I don't know, 10 units by 10 units, the box size is 100 units square, right? And my concentration is 1 glucose per 100 units square, low concentration. I put my enzyme back, and the enzyme is holding glucose in this little pocket. My world, the world I care about, the world to this ligand now is that. It's not leaving the pocket. It's held in there. That's only 1 unit by 1 unit. I still only have 1 glucose. My numerator hasn't changed. But my denominator is now 1 unit squared. 100 times more concentrated, effectively. So to change concentration, instead of adding more chemical, we shrink the space it lives in and increase the effective concentration. This, by the way, also tells us, oh man, I just learned that equation for delta G. How the heck do I account for proximity in that equation? Because there's concentration terms. And often for enzymes, the effective concentration of something will be much higher than you would normally expect. So it gives us a way to relate this abstract concept to math, which apparently isn't abstract by that chain of logic. Good stuff there? So again, enzymes, they stabilize transition states. They have this proximity effect. These are all really good ways to make things happen. I want to now put this into a concrete example. So don't worry about this slide. I want to put this into one of my favorite concrete examples, which is about the chemical acetylcholine. Does anyone know what acetylcholine is? I mean but what it does in the body?
Is it pyruvate?
It's a neurotransmitter. There's something similarly named in pyruvate, so you're on the track. But it's a neurotransmitter. Does anyone know its main role? It's okay if not. That's why I'm here to teach.
Neuromuscular junction.
Neuromuscular junction. Nice. It's the main neurotransmitter that when I think, lift my arm, and that message transmits down my trunk neurons, down my CNS, at some point a neuron has to touch a muscle and tell the muscle, twitch, damn it. Darn it. Ooh, it's almost spring break. It's getting bad. Has to actually convey that neurological signal to the muscle. And the chemical messenger that's used to convey that signal to the muscle is typically acetylcholine. In people with Parkinson's and some other diseases, this process is messed up. So acetylcholine's normal role, I could just live in a room of whiteboards. Wouldn't that be amazing? It's all I really want in this world, just whiteboards everywhere. So if, again, we imagine, my cute little stick figure. I have an idea. I have a little light bulb. I should lift my arm. Light bulb. that message gets conveyed down my musculature to the muscle, and for the nerve to convey to the muscle what to do, it releases this chemical acetylcholine. And what that actually looks like is right here. We have a motor neuron, so this is the end. We have all our CNS, all the way to my brain coming this way. We have a motor neuron that comes in really close contact to a muscle fiber cell. It doesn't actually touch. It's like two siblings on a road trip in the back seat. I'm not touching, right? Like it's really close, but doesn't actually physically touch. And it forms this junction where there's very close to touching, but not quite touching, called our synaptic cleft. It's where a synapse forms. And this is where we need to exchange information. The signal traveling in the neuron has to be conveyed to the muscle cell. And it has to pass this gap. There's no physical connection. It has to pass. And we do that by releasing acetylcholine. So the neuron releases a vesicle, or actually many, many vesicles, full of acetylcholine. This space between the synaptic cleft becomes full of acetylcholine. And there are receptors on the muscle cell that bind to and notice that acetylcholine. Works pretty well. Let's zoom in. Enhance. Enhance. Again, little vesicles of acetylcholine are migrated to the surface as part of the synaptic transmission. They bleb off, they open, and acetylcholine gets transmitted. And unfortunately, I love this slide, except for the fact you can't read it. There are two proteins down here. One is the receptor. It's R in incredibly hard to read font. And one is ACHE with his acetylcholine esterase. And it turns out we need both these functions on the muscle cell. The receptor senses, binds to the acetylcholine and triggers intracellular calcium changes in the muscle cell that cause it to flex. But here's a problem. I had the idea to flex my arm and show off my little olive oil, like, you know. Had the idea to flex my arm. The muscle cell was told to flex. I'm going to be like this for the next 32 years. The muscle cell needs to reset. It needs to know that it no longer needs to flex. And the predominant way we do that is by getting rid of the acetylcholine. As long as acetylcholine is in the synaptic cleft, I'm going to keep twitching. So I have to get rid of the acetylcholine. And the enzyme that gets rid of it is this ACHE, acetylcholine esterase. What it does is it breaks acetylcholine in half, and then the nerve cell reabsorbs those two halves, remakes it into acetylcholine, and prepares it to be released the next time you want your muscle to twitch. It's a very fast process. A good example of how fast muscles can work is hair. Talking, you are flexing and unflexing muscle tissue dozens of times a second. Blah, 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 right? And looking like a freak while you do it. Just keep your mouth shut. Blah, 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 blah. So this is a really cool and actual interesting system, and there's a lot of interest in this because in things like Parkinson's, this acetylcholine esterase sometimes isn't functional. And that's why we get Parkinson's. You get repeated twitching because the acetylcholine concentration doesn't drop as it's supposed to. Yeah?
Is there glycine involved in that? Because is it like...
No, sorry. I meant continue your question.
Because I know with like tetanus, it like blocks the receptors, so the glycine can't be released to release the acetylcholine.
Yeah. That's a really good question. I don't know for certain. It's a really good question. Probably is my answer, but I don't want to put my reputation on the line. What little reputation I have. And so this enzyme that breaks down the acetylcholine once it's done its signaling is very important. So if we look at that reaction, this is what ACHE is doing. It's taking acetylcholine and reacting it with water to break it down into choline and acetic acid. Again, here's our choline Here's our acetate, so we call it acetylcholine. We're just going to break into choline and acetic acid. This involves water. This is a favorable reaction.
Do we need to know this reaction by any chance?
Yeah, this one's worth knowing. So yes. No, it's a really important one. Sorry, we're going to step back. So this is a favorable reaction, because if it wasn't favorable, it couldn't happen. Enzymes don't change favorability, but it's very slow. And so acetylcholine esterase helps make this go. And it does it through both covalent catalysis, electrostatic catalysis, and acid-base catalysis. It does not involve metal ions, but it basically does everything else. So it's a good example for most things. And so we're going to look at it. Again, if we imagine our, wow, that's not a good start. If we imagine our little synaptic cleft where we've got our muscle cell down here and our nerve fiber right here. Acetylcholine esterase is right here. It's embedded in the membrane of the muscle fiber cell. It's a large protein. I can't remember exactly, but I think it's about 800 amino acids. So it's a big protein. We're going to ignore most of it. A lot of it exists. A lot of the amino acids in it are to insert and hold it into the membrane, to serve as a functional part that will signal the interior, or sorry, that's the receptor. No, sorry, a lot of it is to hold it in the membrane, to hold its structure compact. We're going to look at just the little Pac-Man mouth, just where it is binding and doing the active chemistry. And that little piece of a protein, where we expect ligand to bind and chemistry to happen, we typically call the active site. So I'm not going to draw all 800 amino acids. I'm going to draw like 7 right in the active site. What's up?
Is this considered like inhibitory or?
It is not considered inhibitory. It's just a recycling function.
Okay.
The whole, in terms of the whole cycle, it's a reuptake mechanism.
Okay.
So an example of that would be in your brain, you have serotonin reuptake channels. And if your serotonin level in the synaptic cleft is too low because the reuptake system is working too well, or you don't have enough serotonin, you take a selective serotonin reuptake inhibitor, like Zoloft or Prozac, to shut this process down. So it's a reuptake system. Good question. So we're going to look at this little active site. Boop! There it is. We're going to look at 4 amino acids. Again, to give context, up here is protein. This is our acetylcholine esterase up here. And down below it is buffer or whatever have you. This is my protein, ACHE. Up here and down here is like buffer, what have you. The exposed synaptic cleft. And there are 4 amino acids that we're going to care about. A glutamic acid, and again, I'm not showing all its carbons, I'm just showing the business end. An aspartic acid, a serine, and a histidine. 3 of these you should know really, really well. If you haven't learned histidine yet, it's time you did. Because histidine tends to play a lot of important roles in enzymes. And here's why. Histidine, which to me always looks like a little house or something, right? Yay, histidine. Histidine, I just like saying histidine. I'm going to keep saying it. Histidine, histidine, histidine. Histidine. Histidine has 1 nitrogen that we don't much care about. It's already protonated, it's done. But this nitrogen on histidine is pretty unique as far as side chains go, because it can become protonated. We can have an alternative state where we have a positively charged histidine. So it can become protonated. Here's a number that's worth memorizing. Here is a number that's worth memorizing. It has a pKa of about 6. This guy has a pK of about 6. That makes it really, really reactive. Because carboxylic acids that have a pK around 2 or 3, when you're at pH 7, they're deprotonated. Like they're 5 orders of magnitude deprotonated. You're never going to protonate them really. It's going to be really hard and really rare. And our traditional amino group, like we'd see on lysine, pK of like 9.5. At pH 7, it's protonated. You're always going to be protonated. But with a pK of 6, you got a lot of wiggle room. This guy is relatively easy to protonate and relatively easy to deprotonate around physiological conditions. If you want to think as an organic chemist, it is an excellent proton source and an excellent proton sink. It's really good for giving and accepting protons under our reaction conditions. I would estimate over half of all enzymes you will ever see in your life, this is really easy if you're never going to see one again, have a histidine in the active site. It's incredibly common because of that pKa that makes it really easy to donate or lose a proton under physiological conditions. Good stuff there? Other thing we can notice here. I just said this is hard, and yet I did it. I drew this aspartic acid protonated. This is hard. To make this happen, in what's not shown, there are dozens of amino acids surrounding this, lowering the effective pH. Changing the local environment right here to make it such that this guy can be protonated. So there's a whole support structure of other amino acids piling on with the proton density so that it can actually be protonated. And so we see, even though we're at physiological pH, this guy is protonated. That's kind of weird, but it happens. So, roll with it. And this is our mousetrap. We're now set up to do our job. It's going to be our enzyme condition. Ready for the fun? I'm ready. When our substrate, when our ligand comes in, here's my acetylcholine. Acetylcholine has a quaternary ammonium. This thing is obligate positive charged. It's always going to be positive forever and always. We have a negative glutamic acid. They form an ionic bond to hold it in place. Electrostatic catalysis. They form some kind of non-covalent interaction to hold this guy in place. Chunk. And holding it in place puts it in the right position, puts it in the right proximity for the next step. Because now, this ester linkage is right next to some other amino acids. Right? It kind of locks it in place. It's like a magnet or a tractor beam. We're going to do some more Star Trek today. That holds it in the appropriate place. As a reminder, here's what we want to do. We want to cleave this ester bond. That's our goal from the get-go. Make acetic acid on one end, make choline on the other. This is the bond we want to cleave. Well, I've got a carbonyl here. This carbonyl probably has a partial positive charge. It's very electrophilic. So I need a nucleophile. Where, oh, where will I find a nucleophile? The serine could be a nucleophile, but OH is not great. Nitrogen has a lone pair too. Here's how the body decided to do it. Have that nitrogen deprotonate the oxygen. That creates this nice oxyanion, right? It creates this nice hydroxyl attack guy, hydroxide, which can then attack. What did we just witness? This guy was used to abstract a proton, steal a proton. Acid-base catalysis. If you're moving protons around, you're dealing with acids and bases. Acid-base catalysis, jazz hands. And then